Hello students, welcome to the class. So today we will do the NCERT Exemplar of the chapter Chemical Bonding and Molecular Structure. In this session we will be seeing question number 1, 4, 5, 24, 33, 35, 36, 59 and 66 of the NCERT. So here is your first question. Question says that isostructural species are those which have the same shape and hybridization. So we are given a definition of isostructural species here, which says that the shape and hybridization should be same. Now both of the things should be same, and the second term is the most important one, because in some cases you will get the same structure or the same shape but different hybridization. Okay, now you have to identify on the definition of this on the basis of this definition that which of the given set of molecules are isostructural. You have some time to solve this question. Your time starts now. How you will do it? So it's very simple. Just go with the procedure that I have already explained in our previous classes. So your time is up. Just think about it, and if you are getting your answer, you can write it and then check it with my answer. So let us look at the correct answer. So the correct answer will be BF4 minus and NH4 plus. Now going with other options where it was written of BCl3 and BrCl3, then we have NF3 and BF3. If you look for the NF3 and BF3, then there the shape of the NF3 is what? It is trigonal pyramidal. Structure is what? Structure is tetrahedral, right? So neither the and if you talk about the BF3, so BF3 has a sp2 hybridization, whereas NF3 has a sp3 hybridization. So NF3 and BF3 will absolutely not be the answer. If I talk about the BCl3 and BrCl3, then again BCl3 will have a hybridization of sp2. You can calculate the steric number, it will give you 3. Whereas if you consider BrCl3, then there the steric number will be, so 3 will be coming from Cl and 4 are left, so 5 will be the steric number for the BrCl3 molecule. Now that will give you the shape of seesaw. Okay, it has a seesaw shape. So this will also will not be the answer. So the answer will be BF4 minus and NH4 plus. So let us use our formula to first of all calculate the steric number, which is half into V plus M minus C plus A. Just go through the basics. It's very simple. So what are the terms here that is being used in steric number? The first is V, which is number of valence electron on the central atom. Then we have M, which is number of monovalent atom that has a valence of 1. After that, we have C as the cationic charge, and lastly A as the anionic charge. Okay, so let us apply this same on both of the molecules. First, we will start with the BF4 minus. So for BF4 minus, if you calculate the steric number, then the valence electron on boron will be 3. Then the number of monovalent atoms is 4, because fluorine is a monovalent atom, and 4 is the count of this given in BF4 minus. Okay, now moving on to the next thing, which is charge. So there is one anionic charge. If you see, it is given here, a negative sign is being given here, so the anionic charge will be 1. There will be no cationic charge, so we can use this and put it in the steric number formula to get the value as 4. Now we have the steric number of 4. So we have the geometry as, or the shape as, tetrahedral. Okay, so for BF4 minus, which will be sp3 in hybridization, for the steric number of 4 will be tetrahedral in shape. Okay, so I hope this is clear to you for the BF4 minus molecule. Now we will move on to the next molecule. What is that next molecule? It is NH4 plus. What about NH4 plus? Again, we have the formula. So if you calculate the steric number using that formula, so nitrogen will have 5 valence electron, out of which it will have bonding with 4 monovalent atoms and 1 cationic charge is present. So V plus M minus C plus A, we put all of those values, which will give you 4 again as the steric number. Okay, so since 4 is the steric number and there is no lone pair on the nitrogen, if you see, because all of the electrons are involved in bonding with the H. You can try to draw the Lewis structure. So here I have not shown it again because we have already seen it multiple times. So if we are knowing the steric number and if we are knowing that in NH4 plus there are no lone pairs, so we can write for steric number 4, the hybridization will be again sp3 and the shape will be tetrahedral. So this will be your NH4 plus molecule. So I hope this question is clear to you. So if you have a doubt, you can ask it. Now moving on to the next question. So this question is somewhat tricky. So previous one was simple to solve, but in this question you have to decide on the basis of hydrogen bonding and the number of hydrogen bonds. So two things are there. You have to decide the strength of hydrogen bonding, and second thing, you have to look for the number of hydrogen bonds. And on analyzing both of these aspects, you have to say that what will be the correct order of boiling point for the given compound. So we have 3 compounds arranged in 4 different variations, which is the compounds are HF, H2O, NH3, ammonia, water and hydrogen fluoride. So your time to solve this question starts now. So you have to, again I am repeating it, you have to consider 2 things. Strength of hydrogen bond, which will again depend upon polarity, and second thing is number of hydrogen bonds. So your time is up. The correct answer will be B. So water will have the highest boiling point, then there will be hydrogen fluoride, and lastly we will have ammonia. Now if you consider the strength of hydrogen bonding, so I have told you to consider 2 aspects and it is given in the question straightforward. First is the strength of hydrogen bonding. Now on the basis of the electronegativity, we can say that fluorine is the most electronegative element and hence it will form the strongest hydrogen bond. But the story doesn't end here. We have another aspect to be covered, which is number of hydrogen bonds. Now it is seen that your H2O molecule is linked to 4 other H2O molecule, and as a result we have greater number of hydrogen bonding. Although the strength is less, but due to this 4 available hydrogen bonding, the H2O is having the highest boiling point. Okay, how we will see it, how the 4 bondings are possible. If you look at a water molecule, it has 2 lone pairs. Okay, the oxygen has 2 lone pairs and there are 2 hydrogens. Each of the hydrogen will be attached to 2 different water molecule through hydrogen bonding. So 2 hydrogen bonding from here, and your oxygen has 2 lone pairs where each lone pair will be attached to one hydrogen separately. Is it clear? So again I am repeating it. If you consider a water molecule, so it has 2 lone pair on the oxygen atom and 2 hydrogen atoms. So the 2 hydrogen atoms will be linked to the oxygen atoms of 2 different water molecules, and that oxygen atom which is having 2 lone pair. So through this 2 lone pair, it can attach to 2 different hydrogen of 2 water molecules again. So that will result in total of 4 hydrogen bonding in a single molecule of water. I hope this point is clear to you. So as a resultant of this 4 hydrogen bonding plus intermediate strength of the hydrogen bond, which is between NH and HF, it is having the highest boiling point. Now again, remember, still the strength of hydrogen bonding is greater in HF, but due to the extra count, H2O is dominating in the boiling point page. As usual, because of higher electronegativity of HF, and a second thing, that 2 other HF molecule can be present, or you can say it can be hydrogen bonded to 1 HF. So as a result of these 2 factors, which is count of 2 hydrogen bond and strong electronegativity effect, the hydrogen fluoride has the second highest boiling point. What about the third molecule, which is NH3? So although it has a lone pair, okay, but due to its low strength of NH hydrogen bonding, it has a strong weightage of its boiling point. Okay, so it is having the least value of its boiling point. Therefore, we got the order highest for H2O, then the HF, and lastly the ammonia. I hope this is clear to you. So overall, what you can say, so first of all, I think you should remember this order. So because it is a resultant of 2 factors. So whenever you see the final order as a resultant of 2 factor, it is difficult to summarize the result. So in that case, I would suggest that you should remember the order directly. Of course, you should remember the reason as well, but you should remember the conclusion along with that reason. Okay, now moving on further. So our next question is, you have to calculate the formal charge on a PO bond. Now this PO bond is indicating the PO single bond. In the case of PO4 3-. So 4 options are there. How you will do it? So it's very easy. First of all, draw the Lewis structure, right? And then use the formula of formal charge to calculate the same. Okay. So your time starts now. Your time is up. So the correct answer will be -1. Now student make a mistake here. They take out the average formal charge. Now remember this thing. There is no such thing as average formal charge. Yes, there can be a bond order which will be in fraction. There can be never a case of average formal charge. So never calculate it. And in this, you have to calculate it for a specific type of PO bond, which is single PO bond. Now, how do we know? Why are we saying it a single PO bond? For that, let us look at the structure of PO4 3-. If you look here at the structure of PO4 3-, then 2 kinds of bonds are possible between phosphorus and oxygen. And what are those 2 kinds? So the 2 kinds are single bonded O and double bonded O. Now your task is to first of all write the formula for formal charge, which is given as total number of valence electrons in the free atom minus total number of non-bonding electrons minus half of the total number of bonding electrons. So this is the simple formula to calculate the formal charge. As I said earlier, we have 2 types of oxygens that are present in our PO4 3- molecule, which is double bonded O and single bonded O-. Now let us calculate for both of this. So I have calculated for both of this, but we have to calculate for specifically for P single bond O, not for both, but I have given you it for the both. First of all, I will calculate it for the O minus, which is single bond. In the case of oxygen, if you take the number of valence electron, then it is minus, it is 6. Okay, so in the case of neutral atom, oxygen has 6 electrons. What is the number of non-bonding electrons? It is 4. Okay, you can see it here. Then number of bonding electrons, again it is 4 for the oxygen. Therefore, your formal charge will be 0. So here we are calculating it for the double bonded O, not for the O minus. See, because we have taken the number of non-bonding electrons as 4. You can see on the double bonded oxygen, there are 4 electrons which are not bonded. What is the number of bonding electron for this oxygen? As it is making 2 bonds, so total electrons involved in its bonding is 4. Okay, we simply put it in the formula and we get the formal charge as 0. I guess this part is clear to you. Again, I am repeating it. It is for the double bonded oxygen. Now moving on to the single bonded oxygen. So this will be double bonded for O double bonded. If I move for the single bonded oxygen minus, then we know that the number of valence electron in the neutral oxygen atom will be 6. Then looking at the structure, we can say that 6 electrons are present which are non-bonded. You can count it 1, 2, 3, 4, 5, 6, and 2 bonding electrons are present because your O minus is making a single bond. So 1 bond is equals to 2 electrons. Put this thing in the formula of formal charge. So we have number of valence electron minus the number of non-bonding electrons, which is 6. Then we have the number of bonding electrons, which is 2. We will take half of that, and that will give you a formal charge of -1. So from here, we can say that for each P single bond O, there is a charge of -1. Okay, moving on to the next question. In this question, you have to say that which of the following attain the linear structure. So this question is a multiple choice question with more than one answer type correct. Okay, so there can be more than one answer that can be correct. You have to look for each of this. So your time starts now. Just first of all draw the Lewis structure, then calculate the steric number, and then accordingly give their structure. Okay, your time is up. So I will suggest you to at least write the answer, right? If you are writing it wrong or right, that's a different matter. At least attempt this. Now, the correct answer will be BeCl2 and CS2. Let us look at the solution. If you consider the BeCl2, then in BeCl2, the central atom is B. Okay. Why we are taking B as a central atom? Because it is less electronegative. Now, the valence electron in beryllium is 2. Okay. Number of lone pair is 0. Then number of non-bonded pair is equals to 2. Therefore, we got all the data related to BeCl2. And the Lewis structure will be this, which is having a beryllium, then chlorine on both sides sharing 1 electron. So, from here, if you calculate the steric number, you will get your BeCl2 as linear. I am not showing it again how to calculate the steric number. Now moving on to the next, which is CS2. Okay, if you consider the CS2 molecule, in that the central atom will be carbon. Now this carbon will be taken as a central atom. Therefore, the number of valence electron will be 4 and the number of lone pairs will be 0. You can draw the Lewis structure and see it. It's very easy. Your sulfur will have a valency of 2. So it will make, each sulfur will make 2 bonds. What about the number of bond pair present? It is 4. And this will be the Lewis structure of CH2. Okay, if you calculate the steric number, you will easily get it as linear. So the steric number will come out to be 2. Remember, in this question, it will have, say, no monovalent atom, because sulfur is a bivalent atom which is having a valence of 2. Now here, I have not calculated the steric number, but still I am knowing that your molecule will be linear. How we are knowing that? Because you can see it very clearly that a carbon is containing 2 atoms. So it is basically triatomic. Whenever you see a triatomic molecule and your central atom is having no lone pair, your answer will be always a linear molecule. Okay, again I am repeating it. Whenever you see a linear molecule, okay, and you are knowing that from the Lewis structure that there will be no central atom on the central atom. In that case, always keep the shape and structure both as linear. Okay, one more part. So structure is a similar term used for geometry. Both are used for the say orientation, including both your lone pair and the bond pair. Now moving on to the next question. In this question, you have to look at the shape of BRF5. Okay, so just write the shape of BRF5 by calculating steric number and all. Your time to solve this question starts now. Okay, your time is up. So you have to decide the shape of the BRF5. How you will do it? So first of all, you will calculate the steric number and then you will act accordingly with the help of hybridization and all. So I'm already seeing some answers. It will be square pyramidal, diagonal bipyramidal. So let us see. If you look for the steric number of BRF5, then using this formula of steric number, where V is number of valence electron, M is number of monovalent atom, C is cationic charge and A is anionic charge, you can easily calculate the steric number. So the steric number will come out to be, so first of all, let us write the number of valence electron. 7 is the count. Then we have monovalent atom as 5. Then we have charge as 0. So we can calculate the steric number as 6. Now the question is that if you look at the Lewis structure of BRF5, it will have a lone pair. Okay. Now it is having one lone pair and it is having a steric number of 6. So what we can say about its structure and shape? So for steric number 6 and one lone pair, BRF5 will be sp3d2 hybridized. Okay, you can go and look back at the table. You can see it that if you are seeing one lone pair and 6 steric number, the structure will be octahedral, but the shape will be square pyramidal. Now this is the shape that we will get. You can look here. So 5 atoms are arranged in the octahedral corner and one lone pair is arranged on the left corner of the octahedral, and this gives us the total shape as square pyramidal. Now why I am calling it square pyramidal? There is a square shape formed by the 4 fluorine atoms along with the bromine, and on the top of that we have a cherry type structure of F. If you connect all these fluorine atoms, you will get it as square pyramidal shape. Now we have already discussed about it when we are dealing with the shape and geometry, and we were differentiating with the shape and geometry specifically. Okay. Now, again, I am repeating it. Structure also refers to the geometry. So here also you include both the bonding pair and the lone pair. Therefore, I have used the term structure is octahedral. You can also write it as geometry is octahedral. Now moving on to the next question. Our next question is, why does type of overlap in the following figure not result in bond formation? So there are two kinds of overlap that are given here, and the question is saying that both of this overlap are not resulting in a bond formation. You have to justify it using a proper reason. Just think about the reason. Your time starts now to analyze this question. Okay, your time is up. So if you look at the first figure here, in the first figure, if you see, then the plus is overlapping with the plus. Okay, so the s orbital having a plus phase, and it is overlapping with the plus phase of px. But if you look at the downside, then there is a negative phase of the px, which is again overlapping with the plus phase. Now this opposite phase overlap will result in what? This will result in net overlap as becoming 0. Okay, so there is an increase in electron density due to the plus plus and a decrease in electron density to the plus minus, that will result in 0 overlap again. What about the second figure? Remember this, you can't orient, or you can't overlap a px with a py, a py with a pz, or a px with a pz. There will be always an overlap of the p orbital if they are having the same orientation. So px will overlap with px, py with overlap with py, and pz with overlap with pz. You can think of it, it's very simple. When the negative part will come here, there will be no lobe oriented in this direction of negative part. Think about it, okay? Think about it in a way of crossed line, okay? If you take the axis, two axes, then they will never overlap with each other. As a result of this, the symmetry of px and py is very different, and they will result in 0 overlap. I guess this is clear to you, okay? So you can remember it in a short way that in the case of p orbital, there will be always an overlap with the same orientation. So px with px, py with py, and pz with pz. Now here's a question for you. If I take x as the internuclear axis, then which of the three orbitals, means px, py, and pz, will do a head-on-head overlap with the s orbital? Okay, just think about it. If I am taking x as the internuclear axis. Now, meanwhile, I am moving to the next question. Explain why PCl5 is trigonal bipyramidal, whereas your IF5 is square pyramidal. Your time starts now. So your time is up. You have to say that why PCl5 is trigonal bipyramidal, whereas IF5 is square pyramidal. Very simple. Just calculate the steric number, and due to the presence of one extra lone pair in IF5, it will not have a similar shape as the PCl5. Yes, it is due to the presence of lone pair. So we'll see both of them individually. If you consider it for the PCl5, then the ground state and excited state electronic configuration for the phosphorus in case of PCl5 can be written as this. So we have a 3s full-filled orbital, then a 3p half-filled orbital. Upon excitation, the paired up electron of 3s will go on to the 3d. You can see how it is paired up in the excited state. Now again I am telling it is never a mandation to always excite and unpair the electron, and you will see a similar case in the upcoming question. So from this perspective, your IF5 structure is very, very important. Both your electronic structure and your actual geometry and shape. Okay, it's an important one. Now, 5 chlorine atoms are attached to the phosphorus. It will result in a sp3d hybridization. So this S, 3s and 3 orbitals of 3p and 1 orbital of 3d will do a hybridization to give a sp3d hybridization. Now this will overlap with the chlorine atom to give you the final molecule. So if we have a hybridization of sp3d, then the shape will be trigonal bipyramidal, and that can be also judged with the help of steric number. Because if you draw the Lewis structure of phosphorus, it will have no lone pair, and second thing, it will have a steric number of 5. That will eventually give you the shape of PCl5s trigonal bipyramidal. Now moving on to the next question, to the next part, which is IFF5. So in the case of iodine for IF5, if you consider the ground and excited electronic configuration, then you would see a very important difference here from the previous examples that we have discussed. So in this case, we have 1, 2, 3. So 3 pair are present in the valence shell in the case of iodine. But as soon as we move on to the excited state, only 2 of them are getting unpaired up. Okay, whereas the 5s is still paired up. Okay. Now, as a result of this, you are not seeing an excitation for this 5s electrons. So you should always remember this, that excitation of the electron or unpairing of the electron is never a mandatory case for the any hybridization. I hope this point is clear to you. Now there will be sp3d2 hybridization, due to which there will be 5 atom and 1 lone pair. So this is the lone pair. Okay, due to the lone pair of availability, we are seeing an unpaired set of electrons. Now, moving with this information, we can finally say that due to the sp3d2 hybridization, the resultant structure is octahedral and the shape becomes square pyramidal. So similar to the BRF5, remember we have seen the BRF5 molecule. There also we have the same kind of shape. Okay, only the I is replaced with Br in that case, bromine. Okay, so I hope you got the answer. Now moving on further. Here is a assertion reason type question. So question says that if you are considering the 2 bonds of OH in the H2O molecule, then we see that the energy required to break the first OH bond is equals to the energy required to break the second OH bond. So this is assertion. And the reason is given that because the electronic environment around oxygen is same for the breaking of both the bonds. You have to decide that whether these 2 statements are correct or not, and is the reason correct or assertion correct. Then you have to also decide the reason is correctly mentioned or not. So your time starts now. It's a very easy one. We have already talked about it. Your time is up. So assertion and reason both are false. How it is false? If you consider the correct assertion, then both OH bond will have a different bond enthalpy, because when you break the first bond of OH, you are getting a OH negative molecule. Okay, what you are getting a OH molecule. Now this OH, I would not say it a molecule, I would say species. Okay, so we'll get a OH species. Now in the OH species, there is a completely different environment, and now your oxygen is having an incomplete octet. Therefore, it will be difficult as compared to the first bond to break the second bond. Just think about it. It's very easy to identify. Try to break the bond individually one by one, and you will clearly see that why it is difficult to break the second OH bond. And the reason should be like this, because the oxygen is having a different environment. Okay, upon you break the first bond, you are seeing a different environment for the breaking of the second OH bond, not the same environment. I guess this point is clear to you. Now moving on to the next question. Which of the following molecular orbital has maximum number of nodal planes? We have already talked about the nodal planes. You have to decide that which will have the maximum number. So we have sigma star 1s, sigma star 2pz, pi 2px and pi star 2py. Now those who have looked upon the theory of the molecular orbital completely and accurately, including all the nodal planes and all the positions, you will be easily able to answer this question. Your time starts now. Okay, think about it more. It's very easy, right? So if you have attended the theory classes and listened to the concept there carefully, you must have remembered this thing. Okay, so your time is up. Let us look on to the correct answer now. If you look at the electronic structure of all these orbitals, you will clearly see that the pi star 2py will have the maximum number of nodal planes. So it has two nodal planes. Okay. So first nodal plane is perpendicular to the internuclear axis, and the second nodal plane is along the internuclear axis. Therefore, the correct answer will be D. I hope this is clear to you, right? So we have already talked about it. How does the electronic structure look? And it is clearly mentioned there that it has two nodal plane. Okay. Thank you for attending the session.